As we did last class period, we took a look at how our lifestyle releases carbon dioxide into the atmosphere and the impact that has on climate change. One of the issues that we need to address with climate change is that there is a clear connection between the amount of carbon dioxide that is emitted and global temperatures. And so in order to discuss where that carbon dioxide comes from, research has shown over and over again that combustion reactions, our burning of fossil fuels, is the large source of the carbon dioxide that is emitted into the air. And essentially, for all of us who have heard of combustion reactions or anything that burns, we know that things that burn need to have oxygen, and as a product or as a result, they always will release carbon dioxide and water. So we call that reaction a combustion reaction. It could be any type of fuel that we're burning. In order for anything to burn, it always requires oxygen. And as a product, we have carbon dioxide and water. So that could look, as a chemist would see that as this type of chemical reaction, where I have a fuel. I could use the example of CH4, that's methane, and it uses carbon dioxide or combines with carbon dioxide to produce carbon dioxide and water. Every combustion reaction is the same reaction. The only difference is which fuel it is that you're burning. You might be burning propane fuel, or you might be burning methane fuel. You might be burning all sorts of different types of fuel. However, they always will bond with oxygen to produce carbon dioxide and water. And it's this carbon dioxide that is released from a combustion reaction that then moves into the atmosphere and is causing that climate change that we're seeing at the moment. This fuel that we're burning is a unique type of chemical that's different than a chemical that we have been working with for the year earlier. And we call that chemical a molecule. The last many months we've been working with ionic compounds. But now we're going to be working with chemicals that are called molecules because they have unique characteristics. And those unique characteristics are all based on their electronegativity. And so what we'll be doing is we'll be looking how the electronegativity of an atom affects the bond type. So just to refresh your memory on what electronegativity is, it's something we had just briefly mentioned in the first semester, is that electronegativity is the tendency of an atom in a molecule to attract a shared electron to itself. In simple words, it's the tendency of an atom to gain an electron, not to lose it, but to gain an electron. And maybe the best example we can use is one that we've worked with quite often over the year. Here we have sodium and we have chloride. We know, looking at the model of sodium and chloride, that chloride or chlorine is going to gain the electron because that allows it to fill its valence shell. All right. So in this case, chlorine is more electronegative than sodium is. Sodium is not very likely to gain electrons, whereas chlorine has a greater tendency to gain electrons. And in fact, it does. And as a result, we have sodium having a positive charge, chlorine having a negative charge, and these two are attracted to each other to create sodium chloride. So this is an example that we have commonly used. What you're going to be doing is you're going to be exploring how does an atom's electronegativity affect the bond character, and then later we're going to talk about its molecular polarity. So in order to do that, you're going to be exploring a simulation. The simulation you're going to be working with is a PhET simulation that explores a molecule's polarity. So I'd like you to click the window that allows you to get into two atoms. You are going to probably get a screen that looks like this, where it doesn't have any of these values. Perhaps it does. What I'd like you to do is to start by noticing the electronegativity scales that we have here. I can adjust this meter to either have the atom be more electronegative or less electronegative, and I can do that for this one as well. Okay, so just as a reminder, electronegativity is the tendency to gain electrons. So what you're going to do is you're going to click bond character. This bond character more or less tells you what is more likely to occur. Is the bond between these two going to be more ionic? Ionic meaning that it is going to be able to tear the electron away, one of those atoms, and gain it for itself? Or is it going to be more covalent? And the covalent, you can sort of use the analogy of a tug of war. In a covalent tug of war, it's where two equal forces are more or less pulling at the rope at the same time, in which case they are not able to pull one electron off the other, just as in a tug of war, but instead they share the electron because one is not stronger than the other one. And we're going to explore how electronegativity affects that bond character. So what you're going to do is you are going to click this electrostatic potential. This helps us out a little bit in sort of seeing which regions tend to be more negative and which regions tend to be more positive. And you're going to notice at this point right now, the way that my electronegativity is set up, that the bond character tends to be sort of in between, more between covalent and ionic. That means that there might be some sharing, but there also is clearly not an equal pull from one to the other, because clearly this region tends to be more pink, is negative, okay? And this region, which is more blue, tends to be positive. Remember, a region that's more negative means that it's more likely you're going to find the electrons in this region than you are in this region. And we're always talking about valence electrons in this situation. So what you're going to do in this exploration is you are going to adjust each atom's electronegativity and see how it affects bond character. Does it make something more covalent, or does it make something more ionic? And start finding some patterns. The way that I'd like you to collect data is to actually take screenshots of your different data points, and then based on those screenshots, you're going to be writing a SIRS where you're evaluating what makes something more covalent in terms of electronegativity and what makes something more ionic. So at least collect 5 screenshots of different electronegativities and how it affects bond character.